Hey everyone, so we're going to be talking about the third topic in this thermodynamics section, which is all about heat and the first law of thermodynamics. Basically, what we're going to be focusing on is what's going to happen when we take two materials at different temperatures and how is heat can actually be transferring between those two items. There's a bunch of different ways that heat can actually flow. So, heat typically flows due to some sort of temperature difference, and it will end up causing temperature to increase or decrease. And as we know, temperature is considered as the average kinetic energy of the molecules. One way is through conduction, which is through contact, and for the most part that's actually what we're going to be focusing on, is objects that are coming together and heat is transferring from one to the other. There's also radiation, convection, net mass transfer, friction, and chemical dissipation. Now, as far as how each of these conducts heat, a lot of the ways what you have to do is you have to go back to what we just talked about before with the kinetic theory of gases and the idea of looking at these at the microscopic level. So, for example, with conduction and contact, the way heat is being transferred is through the fact that the molecules end up moving around and bumping into the molecules of the other material that's, let's say, colder than it, causing those molecules to start moving faster, thus increasing the temperature. All right, so back in the day, I don't really know why this was a thing, but for some reason, typically a lot of scientists would always go to the default of anything new, anything that couldn't be seen was a liquid. So scientists knew that heat flowed from one object to another, and they ended up assuming that it flowed as a form of a fluid. And it was called a caloric. That's what the fluid was called. Even though it was found to not really exist, we still kind of use this as a homage unit. We go One unit used for heat is the calorie, little c on this. And it's defined as the temperature to raise 1 gram of water by 1 degree Celsius. Um, Now, because of the fact that the calorie is fairly small, a lot of times we use another unit, which for some completely unknown and odd reason, they call the calorie, big C. This is essentially a kilocalorie or 1,000 little c calories, and it's how we normally measure the energy content in food. So instead of 1 gram of water by 1 degree Celsius, it's 1 kilogram of water by 1 degree Celsius. And in the imperial system, the way we use, or what we use in America, is the units BTUs, or what's needed for 1 pound of water by 1 degree Fahrenheit. Um, so I just want to go back to this whole idea that heat was a fluid. It's actually one of the reasons why we tend to use the word flow of heat rather than like a more common phrase of transfer of heat. This also actually applies to electricity. It's why we call electricity the flow of current and things like that, and even the term current. Uh, One thing that you'll notice if you ever kind of look into the history of some of these contents, you'll end up noticing that any sort of thing that we thought was a fluid at one point tends to have a lot of water like terminology surrounding it. Um, Now, it was found through experimentation that the mechanical equivalent to heat, basically how many joules of mechanical energy relates to how many calories of heat, was found that it was 4.186 joules equals 1 calorie. So you can use this as a conversion. Basically, the thing that's really nice about this is that it actually told us that there is a relationship between heat and energy. This was done through Joule's experiment. Basically, what he did was he took this device, and there was a weight on one end connected to a rope and a pulley, and as the block fell, it would pull the rope, causing everything inside of here to start to rotate. These paddles rotating in the water will start to move the molecules more, causing the temperature to increase. So he found how many joules of work were done as this block falls, and then how many calories this ends up gaining based off the temperature rise, and use that to figure out the relationship. This is why we tend to use the SI unit for energy as a joule rather than, kilogram meter squared per second squared, I believe. All right. So here's the first question. Pause the video. Now, one thing I do want to mention is this will be dependent on your information. So the number I get is going to be slightly different. But I want you to try this yourself. Pause the video, go over, and we'll go over it in a second. All right. So here we want to know how high do we have to climb in order to work off 500 big C calories. What we need to remember is that this is 500,000 little calories. So 5 times 10 to the fifth calories. Then we're going to use the conversion factor that 1 calorie is 4.186 joules per calorie, and we get this number of joules. From here, we know a relationship between energy and height, the potential energy equation, P equals mgh. So set this number in for the work that we do climbing up the stairs, plug in our mass for this, which is why it's going to be different for each person. For me, I'm going to give myself a very slimming 100 kilograms. Unfortunately, with the lockdown, not really as true. But for me, burning off 500 calories would require me to walk up 2,000 meters, or the equivalent of about 12,000 steps. Yep, really high. Depending on your mass, though, I think if you were lighter, you would most likely have to go up even higher. So I guess it's good that I'm a little bit on the heavier side. All right. This leads into something called internal energy. Now, we have to actually define the difference between temperature, heat, and internal energy because they are very closely related, but with differences between them that make them important. So, temperature, as we know, is measured in Kelvin, and it's a measure of average kinetic energy of the individual molecules. Now, even though we call it's as a measure of the average kinetic energy, it is not an actual type of energy. It's its own thing. It's measured in Kelvin. We have internal energy, which is seen as the total energy of all the molecules. So this is looking at all the molecules and adding up all their energy. Heat, on the other hand, is how much energy gets transferred from one object to another based off of temperature difference. So internal energy is how much energy an object has, while heat is how much that actually gets transferred from one point to another. Now, the equation for the internal energy for an ideal monatomic gas, monatomic meaning one atom. So, trying to think of something that's monatomic. I'll go with hydrogen, but one single hydrogen atom, nothing else. The equation we have for this, well, as we know, internal energy is the total energy of the system. So what we say is that each molecule has an average kinetic energy of 1/2 mv squared times it by n, and we get this 3/2 nkt, or 3/2 little nRT. So this is the equation we're going to use for internal energy. One thing to note is that this 3/2 is actually important specifically for the monatomic gas. We'll mention this later on, but there is a slight difference in this equation if we start dealing with stuff like diatomic and triatomic. Now, the reason why we're specifically focusing on monatomic gases is because this kinetic energy that we're looking at is pretty much limiting the motion of the particles. See, a monatomic gas is only allowed to be excited translationally. So it can move horizontally, it can move vertically, it can move in the z-axis, in and out. Diatomic and triatomic atoms, on the other hand, can actually be excited past this translational motion. it can start vibrating and rotating. So in those cases, the equation will have to change because there's other ways that it can express its energy. All right. We have a thing called specific heat that relates to basically how the best way I can almost describe it in layman terms is that specific heat refers to how resistant an object is to changing its temperature. So heat flows into an object, and that's going to cause its temperature to change. But as we all know, some objects will change their temperature easier than others. You put a water, like a bunch of water on a stove, it doesn't. It takes a while for it to heat up. But on the other hand, you put a fork on it, and metal fork, and it heats up very quickly. Those two items have different specific heats, which causes them to heat up at different rates. So the equation that actually tells us how much an object will actually change its heat based off of how much heat gets added um, is this equation, Q equals mc delta T. So Q is how much heat that was transferred either to or from the system. M is how much mass it has. C is going to be our specific heat, which is item dependent. And then delta T is our change in temperature. Now, one thing to note is that this change in temperature can be in either Celsius or Kelvin. Um, so just keep that in mind. Yeah, so it could be either in joule. The specific heat can be measured as joules per kilogram Celsius or kilocalories per kilogram Celsius. Depends on what unit you're using or want for Q. Now there are other types of specific heats. There's a constant volume and a constant pressure, but that's something that we're going to briefly discuss later on. But here you can see the specific heats. So for example, something like lead or mercury have very low specific heats, which basically means that they're going to change their temperature very quickly and requires very little energy. For the most part, about 100 joules of energy to change its temperature. But when we look at something like liquid water that has a specific heat of 4,000, that basically means it requires nearly 40 times more energy as lead and mercury in order to change its heat by the same amount of temperature. All right, so here's the first question. I want you to pause the video and work on this yourself, and we'll go over in a second. All right, so what we're going to do is basically use Q equals mc delta T. The first time we're just going to treat the vat as empty. So that's pretty easy. We just look at the 20 kilograms, use the specific heat for iron, plug in our temperature difference, and we get 720 kilojoules. Nothing too crazy there. But now when we add in the vat, well, we have to do the same equation again for the water, and we'll notice that the temperature has been risen to, the heat needed has been raised to 6,000 kilojoules. However, this is not my answer because that's just the water in the vat. We still also have the vat that's increasing temperature as well. So when we add the 720 to that, we get 7,400 kilojoules. So basically, it becomes 10 times more energy needed than when it was empty. Now, this actually leads into a very interesting thing. Basically, if you've ever wondered, I'm pretty sure I brought this up before, but if you've ever wondered why water is always the holy grail for people looking for life, why can't it be any other liquid? Why can't life originate from some other liquid? Why does it have to originate from water? The reason, or one reason at least, is that water has a very high specific heat, meaning that it is a very stable environment for life to grow. That when the sun goes down, while everywhere else it will start to get very cold, in the water it actually can maintain that temperature for a while. So it's not drastically going from boiling hot to freezing cold like it would on something like Mercury or even on the moon, between when it's facing the sun and facing away from the sun. So it makes it really nice for that reason. Um, it's also one of the reasons why water's temperature tends to lag the season by about a month. What I mean by that, if you've ever noticed that right as we start going from spring into summer, when it starts getting really warm, a lot of people start flocking towards the beach or flocking to their pool. You may notice that the water is always freezing at those points. Now, usually it's fine because the ambient temperature, the environment is still hot, so that cold water kind of feels good. But the thing is, the water requires a lot more heat from the sun before it can actually increase the temperature to a more comfortable rate. So, usually in the beginning of the summer or late spring, the water is freezing cold. But then once you also get to the end of summer and you start going into September and October, when we start going into fall, you may notice that if you do go to the beach and it's not super windy, the water will actually still be fairly warm because it still retains that heat. So water is very stubborn in that it doesn't like changing its its temperature that much, and requires a significant amount of heat to change it. All right. So this leads into a very, very nice, important, and in my opinion, fun aspect of heat, which is called calorimetry. Now, in order to talk about calorimetry, I'm going to need to define a few terms. So, one of them is a system. Now, as you've probably learned in other classes, a system is what we define as an object or set of objects that are what we're looking at, that are interacting with each other. So, for example, when you're sitting in your car, if we're going to be looking at you and the car, that's a system. If we're not going to ignore everything else. The rest of the universe outside of that system is referred to the environment. So the system is just what we're looking for, and the environment is everything else. Now, there are different types of systems. There's a closed system, which is one where there is no mass being exchanged between the system and the environment. Now, there could be energy being exchanged, but there's absolutely no mass. Uh, a good example of a closed environment, or a closed system, sorry, would be a pot of water with a cover on top. And a lot of those, I mean, I know in a perfect world at least, um, the mass, the what's inside, all the water would not be able to escape into the environment. But you could still have the heat being radiated from the pot into the environment. So eventually that water will end up cooling down because of losing heat to the environment, but it shouldn't lose any mass. An isolated system is one that's actually a little bit more extreme. It basically means that there's no energy being exchanged either. So this would be a pot with water that's in a vacuum chamber. So all that heat that is inside of that pot cannot leave the pot. So no matter how long you have it in there, it's going to retain that heat forever and ever. So that's what an isolated system is. Now in calorimetry, we're actually going to assume that our system's isolated. There's going to be heat being transferred to and from the items involved inside the system, but there's no heat leaving the environment to the environment. An open system, on the other hand, is just chaos. Basically, mass and energy can exchange freely. That going back to the pot case, this essentially is just having the pot without a lid. So not only is the energy being able to leave the system, but you also have water leaving forever and never really coming back. Now, conservation of energy tells us that when we have an isolated system of, you know, two objects, let's say, that any heat lost by one object has to be gained by the other object. So that's what conservation of energy is telling us. Whatever heat we lose, something has to gain it. So if we have a spoon in a cup of water, if the spoon loses heat, the water has to have gained it. So another way of saying is that the energy in of one part has to equal the energy out of the other. Um, yeah, so it's a very important thing. It's typically things in conservation of energy that you have to worry about, of always asking yourself, where is the energy coming from and where is it going? All right, so here's a question I want you to work on. Pause the video, work on this stuff, and we'll go over it in a second. All right, so here we have some tea that's at 95 degrees. It's being poured into a cup at 25 degrees, and we want to figure out what is the final temperature that they're going to end up reaching as heat gets transferred. So because this is the hotter object, this one's going to end up losing heat, and this one's going to end up gaining heat. Now, we're going to end up using the MC delta T equation for both, so we're going to need mass for both. Now we know what the mass for the glass cup is, we just need to know what the mass of the tea is. Well, since they give us the density and they give us the volume, we can use the density equation, plug the numbers in, and we get that the mass is 0.2 kilograms. From here, I can use the MC delta T equation in conservation of energy to find that those two equations have to be equal. MC delta T for the tea and MC delta T for the cup. Now, before you start, throwing out too many questions, you might wonder, why is the delta T part kind of written weird? Here, it's written as initial minus final. Well, here it's written as final minus initial. There are two reasons for this. Pretty much they're the same reason, but I'm going to explain them in two different ways. First, even though I didn't write it, technically there actually is a negative in here, because if one object is gaining heat, that's a positive energy. If it's losing heat, that's negative. So one of these is actually supposed to be negative. That means that when one of them is final minus initial, the other one is negative final minus negative initial, or initial minus final. Another way of saying that is the way I wrote it, I am assuming that they're positive numbers, so I want to make sure that this delta T is always positive. This cup is going to reach a temperature higher than 25, so it's going to be T minus 25. Well, this T is going to reach a temperature lower than 95, so it's going to be 95 minus T. So whichever way kind of makes some more sense to you, go through it, but just keep that in mind, that one side, that you should pretty much always make it so that these numbers will always be positive. All right, so we plug the numbers in that we have. We do some algebra, moving some things around, and we get that the final temperature is 86 degrees. So we notice that the temperature is much closer to the 95 degrees Celsius, to the temperature that T was at, which again makes sense, because if we looked at the specific heat, the specific heat for T is significantly higher than the specific heat for the cup, about 5 times greater. So it makes sense that it's going to be significantly closer to the T than it is to the cup. This is a good thing to kind of keep an eye out for. What you can do is, when you look at some of these questions, try to come up with a rough estimate or a rough guess of what you think the final temperature is going to be, and then see if that kind of makes sense. If you got that the final temperature is something closer to 25, you did something wrong. And it could be because you accidentally made it 25 minus T or something. All right. So this concept of heat being exchanged from one object to another, and dealing with the whole specific heat, this is related to what we call calorimetry. If you're trying to figure out what's calorimetry and what does that have to do with this. Now, what calorimetry deals with is an item called a calorimeter. Who would have guessed? But a calorimeter is a device that we use in order to actually determine specific heats of unknown objects by mixing the objects. Basically, what ends up happening is that you have a cup. Yeah, you have a cup that is in a somewhat isolated system. So there's some sort of insulation in here. Typically it's air, but it could be other materials. Sometimes they have multiple layers if you want to get a really, really good type of insulating material. Uh, Also, the jacket is sometimes made of like wood or something. Again, something that really doesn't transfer heat that well to make it as much of an isolated system as possible. You have water in a cup, and then you have a little stir and a thermometer. And what you do is you put the unknown material in here, and you make note of what the initial temperature is of the water glass system. Then you stir it around, you measure what the final temperature is, and from there you can figure out the specific heat of the unknown material. So that's what calorimetry is. Now, the equation that we had that we're dealing with before with the conservation of energy can be slightly altered. It's not really a new equation; it's still conservation of energy, but focusing more on the fact that the heated material, the unknown material, it's going to lose some heat, and the heat's going to be gained by both the water and the calorimeter cup. So instead of it being a one-to-one situation like the prior case, it's now going to be a one split to two different materials. But the whole process still ends up being the same. So here's a question. You can pause the video, work on this stuff, and we'll go over in a second. Okay, so that's what we're going to do here. We're just going to do the same thing we did before. So here we do MC delta T for the alloy, for the water, and then for the calorimeter cup. Thankfully, they gave us all the numbers that we needed. No real conversions required. We can actually pull the delta T out for both of these because, hey, they're going to start and end at the same temperature. And then from there, we can start plugging some numbers in. So we plug everything in. The only thing we don't know is the specific heat of the alloy. So that's our only unknown. Move some things around, we do our math, and we get 497 joules per kilogram Celsius. So, yeah. So we can use that, and we'd actually be able to tell what type of material it is, or if it's some sort of, as the name implies, a combination of materials. All right. Now, we need to bring up this thing called latent heat. Now, so far, when we've been dealing with the whole specific heat and that equation, that's dealing with the case where heat's being added to a system to cause the temperature to change. Now, the thing is, that's not the only thing that the object can do when heat is added. The other thing that it could do is also change its phase. So it could go from a solid to a liquid or a liquid to a gas. Now, the thing is, a material cannot do both at the same time. It cannot change its temperature and change phase at the same time. So it's either going to change its temperature using the MC delta T equation, or it's going to change its phase using the latent heat equation. Now, latent heat is essentially the exact same thing as specific heat, but related more towards phase change. So the higher an object's latent heat is, the more energy is required for its phase to change. Here's an example of water and basically what the temperature is as heat is added. So here we see the line going up linearly because they have a linear relationship. But once it gets to that melting point of ice, all of a sudden the heat that gets added no longer causes the temperature to increase, but now causes the phase to change as it goes from water and from ice to water. So during this point, we have like a mixture, a slosh of the two. Once it becomes all water, now every bit of heat that gets added is only put in towards changing its temperature. Once we get to this point, though, the boiling point, now we have all the heat being added to end up changing its phase again as the water evaporates, turns into steam. Then once it all turns into steam, it's changing the temperature again. One thing to note that the specific heats of water in its three phases are all different. So while it may not be super noticeable, these slopes are in fact different. And another thing to note is this: the amount of heat required to actually go from ice to water and from water to steam is drastically different. In fact, it requires significantly more for this point. I think I'm going to mention this in a second, so I'll just leave it at that for now. But latent heat, just like with specific heat, is a material specific and phase specific value. Latent heat is actually represented by a capital L. There's two different types of latent heats. There's a heat of fusion, which is basically used for going from either ice to water or water to ice. The equation doesn't change depending on which direction it's going. All that changes is whether you're adding heat to it, going from ice to water, you're adding that heat, or going from water to ice, where you're removing that heat. And then you have heat of vaporization, which is going from water to steam, or vice versa. So the equation we have for this is Q equals ml. So just like with the other equation, we do have it based off of how much material is involved as well. But again, you could see that the heat of vaporization for most materials tends to be significantly higher than their heat of fusions. Um, so just to see how that equation works, 5 kilograms of water using the heat fusion value right here requires a removal of 1.67 times 10 to the 6 joules from that water into the environment. All right. Before we move on to that question, I just want to say one last thing, and that is that you need to make sure that when you're doing this, if you have a material that's going to go from one phase to another, you have to break it up into three parts. So you have ice that if you have a piece of ice that's being heated into water, what you have to do is you have to take the ice, figure out how much heat is being added in order to get it to the melting point, 0 degrees. Then you have to do the second part, which is actually turning the water the ice into water using the heat of fusion equation. And then you do the third point where the water is now going to the final temperature. So you have to recognize that you have to break it up into every little step. Just like how the material can't just change temperature and phase at the same time, you also can't do the calculation at the same time. You have to make sure you separate into this separate parts. So here's here's the question that deals with that. You could pause the video, work on this stuff, and we'll go over in a second. All right. So for this, before we do this, now I won't really throw this curveball at you, but it is something you have to kind of pay attention for. You need to actually know is what does the phase actually have to end up at? So we can't actually do the calculations yet because we don't know if all the ice is going to melt into water or if the water will end up freezing into ice. Now, by looking at the specific heats, we can actually tell that because the specific heat of water is higher than the ice, double it, typically it's going to require much more ice in order to freeze the water. So if you have something like this where it's 0.5 kilograms of ice and 3 kilograms of tea, you could pretty much guess that the ice is going to melt into tea rather than the reverse, but you still have to double check. So the way we're going to do it is figure out which one requires less energy. The less energy, the more the one that it's going to actually do. So first, let's see how much energy is required to cool the tea to 0 degrees. So to cool the tea, using the MC delta T equation, we plug the numbers in with the T values and we get 250 kilojoules. So that's how much energy is just to bring it to 0 degrees, not to freeze it, just to bring it to the freezing point. So what we're going to do now is look at the ice. Well, how much energy is needed to bring the ice to 0 degrees? Well, using MC delta T, we get that it's 10.5 kilojoules. Now, because this number is lower, all right, so it means that we're going to probably be doing this. But now we have to add in the melting part. So do ml for this, and we get 167 joules. So altogether, it requires 177 kilojoules to heat the ice to its melting point and then melts it all completely. What this tells me is that because this requires less energy, the final temperature is going to be above 0 degrees. So it's going to be in the water phase. Now, if you did this and this number tipped it so it was above 250 degrees, so it was something like, this was 10 and this was 240 or something, what that would tell you is that you're at 0 degrees in temperature, and that it's not water or ice completely. It's kind of hodgepodge. So all you do is just figure out how much heat was needed to actually bring it to that middle point. But now that we know that the final temperature is going to be 0, it allows us to be able to set up the equation. From here, now we know which one is going through the phase change, because it would have been different depending on if it was the water freezing or the ice melting. So because the ice is melting, we have it set up like this. So we have the melting part, the heating to the melting point. Then we have the actual phase change of the ice. Then we have the now water going to the final temperature. And then on the losing side, I guess, you have the T cooling to the final temperature. Now, the good thing about doing what we just did before is that we actually now know these two numbers. So those numbers can be plugged in, no double calculation. But for these two, we use the MC delta T equation, making sure to note the new specific heat for the ice turned into water. And again, the final temperatures are set up so that we have positive numbers. And then we find that the final temperature is going to be 5 degrees Celsius. So the final temperature is 5 degrees Celsius, and it's in the form of liquid water. All right. So this is pretty much a breakdown of the steps you would use to deal with calorimetry, and it pretty much talks about everything that we said. Here, well, first, this is referring to just asking yourself, is it isolated or is there energy coming in and out that we have to kind of take into account. But really, you're doing this type of stuff where you're setting up the conservation energy. You're going to note every single material that is going to gain heat and every material that's going to lose heat. Most of the time, it's only two things, but maybe you have a third or a fourth item. So you want to kind of keep track of that. Use the equations for temperature changes, and if there's a phase change involved, you have to include that ml between the temperature changes. So again, to the whatever the phase temperature required, and then afterwards. So yeah, and then here it says it's kind of the same thing about how the delta T should always be set up so it's always positive. So instead of setting it up so it's final minus initial, set it up so it's high number minus low number. All right, here's the next question. So try this yourself, work on this yourself, pause the video, and we'll go over it in a second. All right, so here we want to know the heat of fusion for the mercury based off of the information that they give us. So we know the final temperature, so we don't have to go through that same business that we did last time. So we're going to set up the equation like this. So we have the calorimeter cup, we have the water, and then for the mercury, we have to split it up into the heating of the mercury and then the melting of it. So melting is going to be the ml equation, and the heating is going to be the MC delta T. When we plug the numbers in for the mercury, we get a little bit over, or a little bit under, I should say, 8,000 joules. Plugging these things into, actually doing the same thing for the calorimeter cup and the water, we can find that the total energy for here is 19,200 joules. Taking all these components together and then solving for this, the latent heat, we end up finding that the latent heat has to be 11,400 joules per Kelvin. Per kilogram. Or another way of writing it is 11.4 kilojoules per kilograms. All right. Sometimes you might also see kilojoules per mole as another unit for latent heat. All right. So going back to the whole, latent heats and how this kind of relates to things like, um, sorry, how this is related to like like what's going on. We kind of have to go back to thinking about the whole kinetic theory. Um, so the whole idea about the latent heats is that as the phase change, so as we're putting heat into a system, we're causing the molecules to end up moving faster. Now, at a certain point, it gets to the point where the molecules in the material will actually have to start breaking from them and loosening the bonds. So in a solid, all the molecules are very tightly connected, and then in the liquid, because of the latent heat, those bonds have now fractured a bit, so they can move a little bit further away. They're freer to move around. So that's what's going on for the latent heat of fusion, that the energy that we're using is starting to break away those bonds, not break them completely, but chip away at it. But then when we look at the latent heat of vaporization, the reason why it's so much higher than the latent heat fusion is because not only are we weakening the bonds, we're also actually completely breaking them. And because of the amount of energy required to completely break the bond versus just weakening it, um, it requires a lot more energy. The process ends up being much more violent than the previous part where we're just kind of weakening the system. All right, so I'm going to leave it at that. And then the next video that we're going to talk about is going to be all about the first law of thermodynamics. If you have any questions, please let me know. Otherwise, I'll see you later.